Good evening. Welcome to Krishna's class. We continue our exploration of some of the consequences of completeness that we proved last time. The nested interval that is confining to the real life. Now, at that time we had a long discussion after that, and we were exploring the avenues for generalization. And we said that if you, in a general metric space, what would happen? First of all, the completeness is an important factor in getting the limit of the sequence that we construct. Therefore, we assume the space to be complete. Then we were talking about nested intervals of the real life. But now what we are going to do is, and they are closed bounded intervals. So we generalize it to see whether the whole thing works with closed bounded subsets which has this nesting property. Then we explored some examples and found that unless we further assume some more things, we may not get the desired, especially in some of the weird metric spaces, like some x with a discrete, or when the natural numbers with the discrete, we can actually show that our expectation, our result as such will not go through. So we need further restrictions. And what is that kind of restriction? And found that of course, the sets have to be bounded. I mean, that's already we are assuming bounded closed subsets of X. That's no problem. But what we need now is, which we didn't require in the case of nested interval, that the sequence of sets should shrink so that their diameter tends to 0. Then only we can assure that there is what you call a non-empty intersection of those nested closed bounded sets. So we shall now formulate the theorem. So we will write down, this is known as the Cantor's intersection theorem. So let us, we shall take up the statement of let be a complete vector space. So completeness we are assuming at the outset. Let a closed, a non-empty for every n belonging to n, such that just the nesting property. Further assume that zero. Consists of exactly one point. This is essentially generalizing the second part of the theorem, and we have what we assert or what we observe through examples is that the first part of the theorem as such cannot be generalized, because this assumption that diameter of Fn goes to 0 is required for our purpose. And why it worked on the real line is that because the special facilities available on the real line, because real line has a lot of structures, and here we are assuming a non-empty set X with a metric defined on it. Then we are just assuming it to be complete. We are talking about what are called closed subsets and having the nesting property. And then we assume further that diameter of Fn goes to 0. There, of course, we could have stopped there. We are talking about closed bounded intervals, and we have the we could have identified the limit using what is called the least upper bound property or the greatest lower bound of the sequence of points. Okay, so let us give the proof of this theorem. Proof is exactly as it is. How do we get the sequence of points which converge? This is the question. So choose xn, because we have assumed that Fn is non-empty, therefore there exists an xn for every n. Now, so we have a sequence. So, X. Okay. For Nm greater than certain n, what we can say is that xn and xm belong to Fn, which implies the distance between xn xm is what? What is happening here is less than or equal to diameter of fl. That's simple. Now you see that we are assuming. Now we are assuming infinity, which implies that dxn goes to 0 as infinity. Okay, and that implies now since x is complete, or x is the limit of the sequence x. Now, so we claim so that okay. X belongs to Fl. Then the sequence and it converges to since Fn is closed, complete, because X is complete and Fn is a closed subspace of X, that is the reason, which implies X belongs to F. And therefore now we prove that suppose tilde then X and X tilde belongs to each other, which implies X tilde is diameter of F. And this is true for every n it follows that distance of X and X tilde, X to X tilde goes to 0, that is X is equal to X. Okay. So that is the argument. So I will just write it out. Can be made as small or given epsilon positive dx x tilde is less than epsilon. Which implies x equal to x. So there is a unique point to which it converges. There is exactly one point which implies singleton X. So that completes the theorem. Now what we want to see is this, or give one more example to highlight the point that if a condition of the kind that the diameter of Fn goes to 0 is not assumed, then we may not have the convergence at all. Now we will look at the example. It's a variant of the example that the discrete metric space that we have considered earlier. So X you take as, now Dmn defined as 0 for m equal to n, and this is equal to 1 plus 1 by the first thing is to prove that this is a metric. So verify that now we observe that any Cauchy sequence is eventually a constant. That means it is Xn is Cauchy if Xn is equal to some x for every n greater than some n. From some stage onwards, the sequence is going to be constant. That is what it says. That is, if that means the tail of the sequence is essentially a constant sequence. I mean, in fact, I inadvertently said that the sequence is a constant sequence when we consider the same example. So eventually it has to be a constant, otherwise it is not going to be, because what happens is, eventually suppose it is not constant, then what happens? See, the distance between two distinct elements is going to be certainly greater than or equal to 1. So it's not, it will fail to be a Cauchy sequence. That is the proof of that. Because you see that this is 1 plus 1 by m plus n. Therefore, dmn is greater than or equal to 1. So if m and n are distinct, then it is going to be greater than or equal to 1. Otherwise, it is 0. So eventually, if it has to be a Cauchy sequence, it has to be reduced to just a a constant sequence from some stage onwards. Okay. Hence, these are the Cauchy sequences. And complete. So that's a complete sequence. Now, what more we need? So let us define now. Now consider defined by right here. N and which is essentially, this you prove that this is the set of all M such that M is so that is Sn. Okay, that means M plus 1 N plus 2 etc. And clearly and you can easily see that in this case intersection over N okay. So if you don't have this diameter of of Sn going to, so here what is the diameter of Sn? Sn is certainly, the diameter of Sn is certainly greater than or equal to, is bounded below by 1. Therefore, it doesn't go to 0. But in that case, you end up with this. I mean, this is a variant of the example that you considered in the last lecture. Okay, so that completes the generalization. And what you should look at is how ideas get generalized. How you prove something on a simple example like the real line. We could get much more than what we could do here because of the special facilities available on the real line, which you don't have on a general set. Here you see there are no structures other than just a metric structure. Okay, and so you need some additional assumption even to get this intersection being non-empty, and then you get that it becomes a singleton eventually. Okay, so that's the case. So thank you very much. So we will continue with our lectures possibly tomorrow. And what we intend to do next is to give a function space example. This is a metric space or a normally linear space, which is not. Thank you very much.